In this video, I want to show you how to do a chi-squared goodness of fit test using any calculator from the TI-83 or TI-84 series. We're going to be using the lists here, and it's going to be very similar to what we did when we calculated expected value from section 6.1. If you have a text, join me on page 648. I'm going to do something unusual here. I'm going to use a prepared example from the text. It's so much easier to follow this if you see a prepared example done using the calculator. So I'm going to do example number 2 right there on page 648. The problem says as follows. An urban economist wonders if the distribution of U.S. residents in the United States is different today than it was in 2000. In 2000, 19% of the population of the United States resided in the Northeast, 22.9% resided in the Midwest, and so on. The economist randomly selects 1,500 households in the United States and obtains the frequency distribution shown in Table 1. Now, when I key this stuff in, I usually follow more or less that format that you see right there actually in Table 2. I like to use the first list that I use for the observed counts and the second list for the expected counts. So let's show you how we put that in. You go to the Stat menu, and you want to use the Edit submenu here because we're going to be keying in some data. Now I have some stuff already stashed in list 1 and list 2, and I don't want to rekey it. So even though it seems kind of crazy, I'm going to use list 3 as my first list here for the observed counts. So we'll just key those in. First one is 274. That's for the Northeast, and obviously we don't key in Northeast, right? It's not necessary. It's understood by the position of the data in the list what it corresponds to. Midwest was 303. South was 564, and the West was 359. Now the goodness of fit test compares counts, and so the next thing we have to do is generate the expected counts. You see those right there in Table 2, but how did that get them? Well, you'll notice that the percentages were given. It said, for example, in 2000 that 19% resided in the Northeast, and so on, and we have a sample of 1,500. So if the counts are the same, then we would expect them to be proportional. So in other words, to calculate the Northeast expected count, which is given in the book there as 285, you would take the percentage, which would be 19%, put it as a decimal, and multiply by 1,500, which is the sample size. And there's your 285. For the Midwest, the percentage was given as 22.9%, so 0.229 times 1,500. And there's your 343.5 you see there in Table 2. And then for the South, it said the percentage was 35.6, so 0.356 times 1,500. And that's the count of 534 for the South that you see. And then finally for the West, the percentage was given to be 22.5%. So 0.225, 1,500. And there's your count for the West. Now we're ready to construct the test statistic. You can see how it's done by hand right there on page 648. We're going to use the calculator to do that. So the first thing we want to do is we want to take that calculation. As you see there, it's the observed minus expected quantity squared divided by expected. And so we're going to construct that list, or we're going to construct that calculation here in this list and populate it automatically. So you go up to the top of the list. As you can see, you want to highlight the top there, and then you want to key in that quantity, observed minus expected squared divided by expected. And remember, list 3 is observed and list 4 is expected. So what you want to do is open up a couple of parentheses, and you want to take list 3 minus list 4. You want to square that quantity, and you want to divide that by list 4. And the list will populate automatically. And then the test statistic itself is constructed by taking a cum sum of list 5 there. So I'm going to go to second stat. It takes me to the list menu. I'll go to ops, and number 6 is a cum sum. So I'm going to take a cum sum of list 5, and that's going to automatically populate list 6. And then as you can see, that last item in list 6 right there, that's your test statistic. That's what you see right there on page 648 as the result of that calculation. Now, the next thing we want to do is get the p-value. And one of the nice things about doing a goodness of fit test is that they're all right-tailed. You never do a left-tailed or a two-tailed goodness of fit test. It's always right-tailed. And so all we have to do is get the chi-squared CDF, and we're going to use that test statistic right there as the lower limit. So I have to quit this. You probably want to jot that number down somewhere. 8.25469. It's possible to retrieve it from the memory, but it's such a hassle. It's just easier to retype it, and it really doesn't change the p-value appreciably. So anyway, let's quit this, and let's go to the distributions menu. And on this calculator, number 8 is the chi-squared CDF, so that's the one we want. And the lower limit, if you recall, the syntax is lower, comma, upper, comma, degrees of freedom. Degrees of freedom is it's the number of categories minus 1. So in this case, we had 4 categories. 4 minus 1 would be 3, so it's 3 degrees of freedom. So anyway, here, let's key this in. So the lower limit would be the test statistic, which was 8.25469. I wrote it down to 5 places. That's fine. And then the upper limit would be positive infinity, so you can just put in 1 times 10 to the 99. That's perfectly acceptable. And then the degrees of freedom was 3. And so the p-value is right there. And just as you can see in the book, the p-value is less than alpha, so we would end up rejecting the null in that case. And what that means is that there's a difference. In other words, things have changed since 2000 for this particular problem. The next example I'm going to take is from the problem set, and it's found on page 652 and 653. Let's clear this. It's actually a rather interesting example of statistics in action. It's problem number 13 on page 652. It's called Benford's Law. Benford's Law is actually used by a lot of people to look for fraud. In particular, the IRS uses this. So when you submit a tax return to the IRS, they screen the digits using Benford's Law, and if they think you're cheating on your taxes, then they'll pull your return and do an audit. Anyway, the problem says as follows. It's number 13. Benford's Law, Part 1. Our number system consists of the digits 0 through 9. The first significant digit in any number must be from 1 to 9 because we do not write numbers such as 12 in the format of 0, 1, 2. So in other words, we never have 0 as an initial digit. Although we may think that each digit appears with equal frequency so that each digit has a 1/9 probability of being the first significant digit, this is not true. In 1881, Simon Newcomb discovered that the first digits do not occur with equal frequency. This same result was discovered again in 1938 by physicist Frank Benford. After studying much data, he was able to assign probabilities of occurrence to the first digit in a number as shown, and it's given there in that table at the bottom of page 652. The probability distribution is now known as Benford's Law, and it plays a major role in identifying fraudulent data on tax returns and accounting books. For example, the following distribution represents the first digits in 200 allegedly fraudulent checks written to a bogus company by an employee attempting to embezzle funds from his employer. Part A is asking, because these data are meant to prove that someone is guilty of fraud, what would be an appropriate level of significance when performing a goodness of fit test? Well, we probably want something very small because our legal system tends to favor releasing the guilty rather than incarcerating the innocent. And so we'd like to really err on the side of caution here, and we'd probably say, something like alpha equals 0.01 would be a reasonable level of significance, maybe even smaller. Anyway, it says, using the level of significance chosen in Part A, test whether the first digits in the allegedly fraudulent checks obey Benford's Law. So if you recall, when you do a goodness of fit test, you're just seeing whether the observed counts agree with the expected counts. And if they do, then you would you would fail to reject the null. If they don't, then you'd reject the null. So in this case, let's test this. Now again, I've got this data already keyed in, so I want to go back to the stat menu, and I've got it keyed in actually in list 1 and list 2. So I probably should, if I want to do this cleanly, I should clear out some of my lists here. Let's go back to the stat menu real quick, and I'm just going to clear list 3 and list 4. so you can see how that stuff is put together. So now I can go back there, and I'm pretty well ready to go here. I miskeyed that there, so now I'm back. Okay. So as you can see, I have the observed counts, which are taken from the table at the top there of page 653. I have those in list 1. And I have the expected counts, which I'm going to show you how to get, in list 2. Now, how to get these expected counts? Well, if you'll notice, the probabilities of the first digits are given there, the frequencies, in other words, at the bottom of page 652. And we have a sample of 200 checks. So where did that 60.2 that you see right there come from? Well, we took the probability of a 1, which is 0.301, and we multiply that by 200. And you can see it's 60.2, and the probability of a 2 is 0.176, and we multiply that by 200. And that's where the 35.2 came from, as you can see. So the rest of the list is populated in that way. Now, in order to construct the test statistic, again, we have to go back to list 3, and we want to take the quantity observed minus expected, square it, and divide by expected. So I have list 1 containing observed, and I have list 2 containing expected. Square that, and I'll divide that by list 2. So that list is then populated automatically. And then I'm going to build my test statistic in list 4, again using a cum sum from the list ops. So you highlight list 4 right there, you go to second stat, go to ops, take number 6, and we're doing a cum sum this time on list 3. And so again, your test statistic will be the very last element in that list right there. You can see it's 21.693. Now again, we could fetch that from memory, but it's a pain, so let's just write it down, and then we're going to use chi-squared CDF to get the p-value. So I'll write down 21.693, 3638, however many places you want to go. In this case, let's take it out one more place there. And I got to quit this. So I'll go to the distributions menu. Number 8 is the chi-squared CDF. The lower limit is my test statistic, so 21.69336. Upper limit would be infinity, so 1 times 10 to the 99. And in this case, if you'll notice, there's 9 categories. 9 minus 1 would be 8, so there's a total of 8 degrees of freedom. And our p-value is given right there. It's 0.0055. So it's a very small p-value. And to answer part C, it says, based on the results of parts B, parts A and B, do you think that the employee is guilty of embezzlement? Yes, I do, because the p-value is so small right there, 0.0055. And again, if you understand what that is, that's the probability of obtaining a test statistic more extreme than the one we got, assuming the null is true. So in other words, the probability of getting that test statistic is very small, and there's a great chance that this person did in fact commit embezzlement. I hope that helps. Again, probably should practice this on your own, so take a couple of problems that are odd from that section right there, and you can use the same method and then check your answer with the back of the book.